Hi there, Year Nines. Today's lesson, I'm going to go through index laws. So you got 8 of them, and in today's lesson, because of my absence, apologies, I'm only going to give you the rules, and you're going to write these as part of your notes, and then in class, I'll explain the logic to it. Okay, so let's start off. When you have a base of a to the power of m, and you're multiplying to another power where it has the same base and a different power, or the same power, doesn't matter. The point is, if the bases are the same, you can simplify it by adding the powers. So here what I'm saying is a to the power of m times a to the power of n is equivalent to a to the power of m plus n. Okay, so that's index law number 1. Here's an example. If I gave you 3 to the 4 times 3 to the power of 5, then simplifying this is equivalent to saying 3 to the power of 4 plus 5, which is 9. Okay, and a reminder, 3 to the power of 4 is equivalent to 3 times 3 times 3 times 3, not 3 times 4. Okay, now let's look at the second rule. Second rule says a to the power of m divided by a to the n. Well then, if you're dividing them and they have the same bases, then it's a to the power of m minus n. An example would be if I flipped it around, I said 3 to the 5 divided by 3 to the 4. Okay, and that would be the same thing as saying 5 take away 4, which is 3 to the power of 1, which we normally just write as 3. Okay, then we go to index law number 3, which is an extension of index law number 1. This one, if you have a to the power of m, but then all to the power of n, this is the same thing as writing a to the power of m times n. Here's an example. If I gave you 3 to the 4 all to the power of 5, this is equivalent to 3 to the power of 4 times 5, which gives you 3 to the power of 20. Okay? And then index law number 4, which is a common, there's a common mistake that occurs, so I'm going to write this down. The law is that it's an extension of number 3, so you do p times the n and then p times the n, right? Because there's 2 different terms there, or powers there. So when you multiply them, most students will know that it's a to the power of m times p, and then times with b to the power of n times p, right? But here's an example that students tend to make a mistake on. I often give students something like 2 to the power of 2 times a to the power of 4 to the power of 5 as an example. And in this case here, a lot of students will only multiply the powers 4 and 5, and they would write 2a to the power of 20. What they're missing, on the other hand, is this 2 is also to the power of 1. So you're meant to do 5 times the 2. Because the rule says, remember, it doesn't mean that it always has to be a letter. It can be a number as well. A has a different base to B. Right now, that's a base 2, and this is a base A. So, of course, the powers you have to multiply to the 5 as well. So it's actually missing 2 to the power of 5 there. Okay, and 2 to the power of 5 is, I think, 32, a to the power of 20. Okay, let's go to law number 5 now. Law number 5 is pretty much similar to index law number 2 and 3 combined. So here we go. We are now multiplying the powers. Okay, we're multiplying the powers, number 3 I meant. So a to the power of m times p over b to the power of n times p. An example of that would be something like, if I used the same idea, if I did 2 over a to the power of 4 all to the power of 5, then you must also recognize that 2 has a power of 1, so it'll be 5 times the 1 and 5 times the 4. You should get 2 to the power of 5 all over a to the power of 20, which is 32 on a to the power of 20. Okay? Next one, a to the power of 0, or anything to the power of 0 is equivalent to 1. Okay, I'll explain why this is the case later on, but this for now, you just need to know anything to the power of 0 is 1. Here's a common mistake that students make. 3 to the power of 0 versus 3a to the power of 0. So the first one, 3 to the power of 0 is equal to 1. But here, 3a to the power of 0 is not equal to 1. This actually means 3 times a to the power of 0, which means 3 times 1, and that equals to 3, because anything to the power of 0, right? But remember, there's a times in between the 3 and the a. Had they given you 3a all to the power of 0, then yes, you are correct. Okay, because within that, it's 3a, and it's all to the power of 0, and that's why we know it's equal to 1 there. So there's a common mistake there. Just copy those notes there. The last two, number 7, I find a lot of students use quite a bit, but I don't encourage it because it gets fractional answers. So here, a to the power of negative m, so when you have a negative power, then you can rewrite as the reciprocal as a to the power of positive m. Here's an example. If I gave you 3 to the power of negative 4, that is the same thing as writing 1 over 3 to the power of 4. Okay, so it's the reciprocal, because 3 to the negative 4 is like saying 3 to the power of negative 4 over 1. And when you write the reciprocal, it flips, and the power becomes a positive. There's a logic to why this works as well, but I'll show it in class. Okay, and the last law, which is the one that students tend to forget, because it involves surds and all that, and we do a lot more in chapter 4 as well in the next few exercises. But here, when you have the nth root of a to the power of m, then the rule is a to the power of m on n. So it means the nth root becomes the denominator of the fraction. So what's an example? If I gave you 5th root of a squared, that is equivalent to writing a to the power of 2 on 5. See how the 5th root has become the denominator? And 5th root just basically means something times something times something times something times something. So 5 times needs to equal to whatever it is that we want, which in this case is a squared. All right, so that's what 5th root is. It's kind of like square root. So when you say square root of a, for example, what that is the same thing as saying something times something must equal to a. Now, when you write the square root, there's a little hidden thing here. Because we know it's square root, we don't actually need to write the 2 at the front. So this is actually the same thing as writing a to the power of 1. So the rule number 8 says this is a to the power of 1 and 2. So when you say square root, it's actually the same thing as writing half to the power of half. And if you said cube root, right, so you actually put a 3 there, then this is actually the same thing as saying a to the power of a 3rd. So on your calculator, if you couldn't do the 4th root, for example, there's no button for the 4th root of a number, you can actually write whatever that number is to the power of 1 over 4. Okay, so that's index law number 8, which you'll find very useful in the next few exercises coming. Okay, all right, so pause the video there, make sure to copy the notes, and then now we're going to do some examples. Okay, so let's do this example over here. When we're doing these examples, I like to encourage students to break the problem apart, especially if you're not very fluent with the index laws. Then this is how I normally teach my students. When you read this question, that's 2ab squared, right? That actually means 2 times a times b squared. And then you've got times 7a squared b cubed, which means 7 times a squared times b cubed. Now, there's a lot of numbers and letters going on there, so I normally like to organize it. I say to students, numbers with numbers and letters with letters. So the a's go with the a's, and then the b goes with the b. So with multiplication, order doesn't matter because we can rearrange them. So for example, 3 times 2 times 1 is the same thing as if you wrote 1 times 3 times 2. Order doesn't matter. You can place it in any order because it's commutative. It's by the commutative law, right? So in this case here, I would say then rewrite your answers as 2 times 7. So keep the numbers as numbers, times with letters, so a times the a squared, times with b squared times b cubed. Can you see how I've kept all the a's together, all the b's together, and then all the numbers together? And in between, the multiplications are always there. So that's times, so here, that's times, which is, sorry, here. And then, so I should have the same number of times 2. So 1, 2, 3, 4, 5, and I've got 1, 2, 3, 4, 5 as well. Okay, so they're all there. All I've changed is just the order. And now if you simplify it, 2 times 7, which is 14, times, again, now we could use index law number 1. The bases are the same, so you can add the powers. So 1 plus 2, when you're multiplying them, you add the powers together, so it becomes a to the power of 3 times, and the same thing with the third example. You're timesing with the bases the same, so it's b 2 plus 3, which is 5, and you can write your answer as 14a cubed b 5. Now technically, I'm meant to write the intermediate steps in between. I was kind of skipping a step there, but technically you're meant to write it as 14 times a to the power of 1 plus 2 times b to the power of 2 plus 3. And that helps remind you what you do with the rules there. Okay, but do that mainly if you are having problems with indices and you're getting them wrong. Okay. Next one, here's my next layout. So as I'm solving for this is likely rule number 4. Rule number 4 and 5 says that when you have a fraction and you've got an extension of a power, you would multiply all of them by the powers. Now, what's a common mistake here? See that 5? That is actually a different base to y, and they both have a power of 1. So you're meant to do 2 times the 1 and 2 times that 1 there too. So it actually is x to the power 3 times the 2 all over 5 to the power of 1 times the 2 times y to the power of 1 times the 2. Okay, so don't forget that 5. That's a common mistake the students don't forget to do. So x to the power of 6 over 5 squared, which we already know is 25, and then that's times y squared. Okay? Let's go to question C, which is now law number 6. Law number 6, you got to be careful with the power of 0, so break it apart. 5 times p to the power of 0 minus, again, this is 2 outside the bracket, so it's 2 times 7p all to the power of 0. Now you can see here p to the power of 0, that's equivalent to 1, and this 7p is all to the power of 0, so that's equivalent to 1. So if you write it out clearly, it's 5 times 1, which is 5, minus, or maybe I should write it like this. 5 times 1 minus 2 times 1, which actually is 5 take away 2, and we know the answer is 3. Common error there is that students will write this as 1, so 5p to the power of 0 is 1, minus 2 times the 1, and then they write negative 1 as the answer. Okay, so just be careful when you're dealing with index law number 6. Now, question D, yes, there's much more complexity. Yes, there is that negative power, and I already mentioned at the start, try not to use law number 7, which is a to the power of negative m, and you do the reciprocal, and it becomes a positive power, because you get fractions. And when you include fractions, it becomes really confusing to do. So I often just stick to law number 1, 2, and 3, and it gets me by most of it. I only start using law number 7 towards the end. Okay, so here, let's do this one. So when I look at this, I break it all apart. I just focus on the numerator first. Okay, so in the numerator, I can already see that there's this bracket, and the bracket is a problem. We want to break it all apart. So to break it all apart, I got to get rid of the brackets. And law number 3, okay, law number 3 and law number 4 gets rid of that bracket there. So I'm going to do that negative 3 times the 2, because remember, law number 4 and 3, you multiply the powers. Now don't forget that y has a power of 1 as well. Okay, so if I break it apart, it's 4 times, now let's work it out. It's x to the power of 2 times with that negative 3 times with y to the power of 1 times with that negative 3. See what I'm doing? I broke it apart. I used law number 3 and 4 to spread it apart. And then times, now 2x is the same thing as saying 2 times x times y to the power of 4. So that's my numerator. Can you see how I've split up all of my terms in the numerator? Well, technically they're all one term, but I'm splitting up the numbers with numbers, letters with letters. Yeah? And on the bottom, it's 2 times x to the power of negative 2 times y to the power of negative 2. Now let's color code it so you can see. So numbers with numbers, 4 times the 2, I'm going to keep them together. I'm going to keep all the x's together, so x to the power of 2 times negative 3, and this is technically x to the power of 1 over here. And then I'm going to collect all the y's, so y to the power of 1 times negative 3, and y to the power of 4. So here's my y's, here's my x's, and here's my numbers. So if you split it up, this is the same thing as writing 4 times 2, so I'm keeping the numbers together, all over. Actually, yeah, I'll take one extra step so you can see what I'm doing. So 2's on the bottom there, times, with x to the power of now 2 times negative 3 is negative 6 times x to the power of 1. Yeah, so I've just did the highlighted numerators. And then times y to the power of 1 times negative 3 is y to the power of negative 3 times y to the power of 4. In the denominator, I've got times with x to the power of negative 2 times y to the power of negative 2. Can you see how I've kept letters with the letters, y's with the y's, and then numbers with numbers, yeah? Now, the thing about multiplication, especially with fractions, you can actually split them up. You can split them up. This times, you can actually rewrite it as times, and what you can do now is you can write this as 4 times 2 is 8 on 2, and then this is x to the power of negative 6 times x1. You add the powers together because the bases are the same. So negative 6 plus 1 is negative 5 over x negative 2 times separately with y negative 3 times y to the power of 4. You add the powers together, so it becomes y to the power of 1. And then that's y negative 2. Now, when you add them together, can you see... Oh, sorry, you simplify them. Can you see now 8 over 2 is the same thing as writing 4 over 1. True? I'm keeping it as a fraction because these are all in fractions rather than just writing a 4. I'm multiplying with... Now, what is x to the negative 5 divided by x negative 2? Well, that's actually law number 2. X negative 5 over x negative 2 is the same thing as saying x negative 5 divided by x to the power of negative 2. Law number 2 says that if the bases are the same and you're dividing them, you will subtract the powers. So it's negative 5 minus a negative 2. And we know that when you minus a negative 2 is the same thing as saying adding 2. So negative 5 add 2 is negative 3. Okay? So when I write that x negative 3, remember that's like, if I wrote that as a fraction, that's x negative 3 over 1. So here you can write it as x negative 3 over 1 times, and we do the same thing over here. That's y to the power of 1 divided by y to the power of negative 2. So y1 divided by y negative 2. That's the same thing as saying 1 take away negative 2, which is y cubed over 1. I'm writing as a fraction because they're all fractions at the moment. Now notice here, that's x to the power of negative 3. We never write our answers with negative powers. So here you can use index law number 7. Law number 7 says that you can do the reciprocal, so the reciprocal, and you rewrite it as a power of a positive power. So this would actually be 4 over 1 times 1 on x cubed. I'm using law number 7 there finally. And then times y cubed on 1. See how I don't do the law number 7 until the very end? And then now, when you're multiplying fractions, top with top, bottom with bottom, and what you get is 4y cubed over x cubed. There you go. So those are good problems to practice your skills there. You can pause the video here just to make sure you practice your 8 law, or more like 7. More 7 index laws is the main ones that you'll be practicing from question 1 all the way to pretty much question 5. That should be enough for you to try out question 1 to 5. Obviously, as you get to 5, you then start practicing all laws together. So it's worthwhile definitely doing question 5. And then once you're ready to get on to question 6 onwards, we go example 2. Okay, so from here, I'm going to assume that you've already practiced question 1 to 5, or you're ready to try example 2 notes. So here, what we can see is the brackets make it look confusing, but what I do is I just simply look at the powers. So here, I can see I've got a power of negative 1, and this is a power of negative 3. And we know that according to rule number 4 and rule number 3 says that if you have a to the power of m to the power of n, you multiply the powers, right? Well, in this case, it means I'm going to multiply the powers over here. So I know that this would then simplify to 2a squared over b to the power of -3 times -1, which is +3. True? Because this here, I don't need to know what that is. I just needed to know the powers. So now that gives me the simplified version. It makes it a lot easier with less brackets. From here, we can clearly see this is now law number, 5? Law number 5 says a to the power of m over a to the power of n, all to the power of p. You multiply the powers, right? So here, we're going to multiply the powers. And remember, this 2 is not just a 2, it's 2 to the power of 1. So you're going to multiply the 1 with the 3 and 3 with the 2. And again, b has a power of 1. You're going to multiply 3 with a 1 here as well. Okay, so common mistake. So 2 cubed times a to the power of 2 times 3, which is 6, all over 1 times 3, so there's b cubed. Write your answer as 8a6 b cubed. Cool. And your final one is an enrichment question. It's a good one to sort of see how you would do these kind of problems and do a bit of thinking. But this is 11C. They tell you that if x to the power 4 is equivalent to 3, they want you to find what 2 times x to the power 16 is. The hint is that because it's x to the power 4, you need to somehow write this expression with an x to the power 4 in it. And one of the things I know is, well, 2 times x to the power of 16. See, x to the power of 16, I can do a bit of problem solving. I can say, well, I need an x to the power of 4, right? But how can I make x to the power of 4 equal to x to the power of 16? Well, x to the power of 4 I've got. I know that's a 3. But I know using law number 3, if I put a 4 on the outside, I know that 4 times 4 will give you 16 because law number 3 says a to the power of m to the power of n is equivalent to a to the power of m times n. True? So I can see there, just even in that step there, I could have broken it up as x to the power of 4 times 4. 4 times 4 gives you 16. And then therefore I can write it as 2 to the power of, 2 times x to the power of 4 with the power of 4. And then that's the same thing as saying, now we already know that x to the power of 4 is equivalent to 3. So this here I can replace with a 3. And now you can work that out. So 2 times 3 to the power of 4 is 81. And double of 81 is equal to 162. Okay, so there's a bit of problem solving there where you use this step where you can break that 16 into something that you're more familiar with. And there's obviously many ways, but your aim was to involve that 4, so x to the power of 4. And the little trick there was to notice that you could use law number 3. And then if you look at 12D, I haven't taught you guys the inverse of exponentials or base indices, but I can teach you how to solve an equation by inspection. And what that means is something like this. If I gave you 3 plus, x is equal to 3 plus 5. My question is, what is x? Hopefully you immediately knew that x had to be 5. Without even doing 3 plus 5 is 8, and then without doing the whole algebra where you have to subtract 3 on both sides, and then you get 5, right? How you knew this was 5 by inspection was by comparison. You said, they both have a 3. Cool. They're both equal. So that means if this is a 5, that must be a 5 as well, logically, because that's a plus and that's a plus. So x just has to be 5. True? Well, the same thing with 2 to the power of 2x minus 3 equals 16. If we can write this equation such that they both have the same bases and it's to the power of something, then I can compare them and equate them. So here, 16, I can write 16 as a base 2. So 2 to the power of what gives you 16? Well, I know it's 2 to the power of, if you didn't know, you can break it up. It's 4 times 4, and then 2 times 2 times 2 times 2, so it's 2 to the power of 4. Yeah, so 2, 2, 2, 2. Now, you can see here, this is 2 to the power of 2x minus 3. Can you see how, by comparison, they both have a base 2, and they're both equivalent? That means this has a power of 4, then 2x minus 3 has to also equal to the same power. So that means 2x minus 3 must equal to 4. Yeah, because bases are the same, so the powers must be the same. Here you can add 3 on both sides, and that gives you 7, and then divide 2 on both sides, so x must be 7 on 2. All right, and that concludes my lesson for today. That should take you pretty much through from fluency skills to problem solving to the enrichment sections as you're doing the questions. Okay, thanks for watching, and in class we'll go through more of the theory as to why these laws work. Okay.